Change. It's a part of most technology. Objects, fluids, electric charge, and heat are all capable of changing in some way, often doing work in the process. Controlling technology, or predicting how it will change, requires a measurement of that change. Usually it can be done by measuring rates, such as speed. But there are other cases where normal rates do not apply, where the type of change requires a different kind of measurement. This is where time constants are used to calculate these types of changes. If an object moves at a constant speed of 55 miles per hour, you can safely predict that in 1 hour it will cover 55 miles, in 2 hours 110 miles, and so on. If a pump moves a fluid at a constant flow rate of 10 gallons per minute, you can safely predict that in 5 minutes, 50 gallons will move. A steady electric current of 10 amps will move 10 coulombs of charge every second. And if heat flows through a radiator at a constant rate of 500 calories per minute, you can safely predict that in 2 minutes, 1,000 calories of heat will flow through it. We have already seen these cases in our unit on rate, but notice how we've said constant speed, constant flow rate, steady current, and steady heat flow rate. These conditions are uniform. The force that causes an object to change its position, the pressure causing a fluid to flow, the voltage causing the electric charge to flow, and the temperature difference causing the heat to move are all constant. So the amount of change that's happening over a period of time is uniform or in a steady state. There are other conditions where the forces are not constant, so the change is non-uniform. An object that is vibrating will come to rest in a non-uniform way because the force is changing. A fluid being compressed into a sealed tank will flow in at a non-uniform rate because the pressure in the tank is changing. When capacitors are charged and discharged, the flow rate of electricity in and out is non-uniform because the voltage changes. And if a hot object is allowed to cool to room temperature, the heat will flow out of the material in a non-uniform way because the temperature difference is changing. In these conditions, you cannot safely predict what will happen over a period of time using simple rates, because the amount of change is always changing. These are the types of conditions where time constants are used to predict how long it will take for these non-uniform changes to be complete. The difference between a uniform and a non-uniform change is easier to understand if we represent it graphically. So here's a question. If you take a checkerboard, which has 64 squares on it, and you place 2 sugar cubes on the first square, 4 on the next, 8 on the next, doubling the number of cubes, so you go to 16, and double the cubes each step and do it once every second, how many sugar cubes would you need to cover the 64th square, which you would get to in 64 seconds? You have 1 second to answer. I'm sorry, your time is up. The answer is not 2 times 64, which is 128. The answer is about 20 billion billion. That's enough sugar to cover the entire surface of the Earth. Surprised? The reason is because the amount of change in each step, the number of sugar cubes, increased in a non-uniform way. If I had said, place 2 cubes on the first square, then simply add 2 each time, so the amount of change was always the same. So if I had said, place 2 cubes on the first square, then simply add 2 each time. So you'd go from 2 to 4, 6, 8, 10, 12, and so on. It wouldn't be very difficult to predict that after 64 squares, you would have 128 sugar cubes. That kind of progression where the change is always the same is called linear. And if you plot that, you always get a straight line. A non-uniform or a non-linear change is when the amount of change in each step is always increasing or decreasing. So when we double the amount each time, we get a different shape of curve. So if we double each time, we go from 2, 4, 8, 16, 32, and then it's not very long before we get to 128 on only the 7th square. But notice what's happening here. 2 is 2 to the first. 4 is 2 squared. 8 is 2 cubed. And then we go to 2 to the 4th, 2 to the 5th. What we're doing is changing the exponent, or the power of 2. So that by the time we get to the end of the checkerboard, we have 2 to the 64th, which is 20 billion billion. That's why the number gets so large. This kind of progression, where you change the exponent, is called an exponential change. And if you plot that on a graph, you get a special kind of curve called an exponential curve. Exponential curves are not always doubling. I could have said take 3 and then triple each time. Exponential curves come in different shapes, and they're very convenient for us because it's a convenient tool to find a time constant. Time constants are a way of predicting how long it will take for an exponential event to be completed. The tool to finding a time constant is this exponential curve. If the curve for any process is plotted, the time constant can be found graphically. Simply find a point on the curve that is 37% of the maximum value. Drop a line straight down to the time axis, and that value is the time constant. If you count over 5 of these time constants, the process has been divided into 5 equal segments of time. After 5 time constants, the process will be 99% complete. Time constants are used in mechanical, fluid, electrical, and thermal systems. In mechanical systems, they're used to measure unwanted vibrations. A vibrating structure can come to rest in an exponential way, called damping. Time constants calculate how long it will take for most of the vibration to damp out. In electrical systems, time constants measure the time it will take to charge and discharge batteries, capacitors, and inductors. Here, the voltage rises exponentially to a maximum value. The change is rapid at first, then the flow of charge into the system slows down as it approaches that value. Time constants calculate when the charging will be 99% complete. Time constants can also be used when the flow of heat is non-uniform, such as when a material like glass is cooling down to room temperature. The flow of heat does not take place at a uniform rate. The heat flows out quickly at first, but as the glass approaches room temperature, the outward flow of heat slows down. Time constants predict when the cooling process will be 99% complete. Here's a case where a time constant will be used to make sure that clocks run at a steady rate. A clock is not supposed to change its rate, but one of the problems in timekeeping is synchronization. Don Sullivan is with the National Bureau of Standards in Boulder, Colorado. He explains how a time constant will be used to ensure that everyone agrees on what time it really is.
Centuries ago, man was content to keep time with an object like this, an hourglass, and pendulum clocks and many other sorts of time-keeping pieces. But today, that's not adequate. What we really do today is keep time with the atom. The atom is really the reference for all of our timekeeping today. The systems behind me are the control console for the National Bureau of Standards time scale, which is calibrated by our primary atomic clock based on the cesium atom. But what we want in these systems is really the regularity of the system. So the frequency is very constant. Now, there are many other systems in science that, for which the frequency is not uniform, but is changing gradually with time. Now, at the level of timekeeping that we're talking about, one example I might mention is the recently discovered millisecond pulsar, a very dense neutron star in space that is rotating at a rate and emitting signals which we receive at the Earth. Now, this object is extremely regular, but it's slowing down. The system is slowing down with something like an exponential decay. To give you an idea of how slowly this is slowing down, it has a time constant on the order of 10 to the 20th seconds. That means that it is something on the order of 10 to the 12 years before this thing reduces significantly in rate. Well, everything I've said might imply that we would really like to use that pulsar as a timekeeper. It's not particularly practical, as I said, but it can contribute significantly to an understanding of our timekeeping on Earth. One has to realize that the time standards that we develop here have no references. As we improve timekeeping, we have very little way to know how well we're doing. So anything we can grasp that lends some additional confidence to our timekeeping is very attractive to us.
Exponential changes are a tricky concept, but if you can represent them graphically, then draw the curve, find the time constant, you can accurately predict when those changes will be mostly complete. Huh? Thanks, Larry.